It sees very clearly. So today is our great pleasure to have Sebastian Tappe speaking with us about Kimberlites. So Sebastian began working on the Mantle since his PhD, and he has a really diverse background in both academia and industry. And since he has been working at De Beers in both Canada and South Africa, so his background is also international. After receiving his early academic training in Germany, Sebastian moved to Canada, and then he moved to South Africa. So today is going to talk about the work that has been working on in the recent years on kimberlites, in particularly tungsten isotopes. So with that, I'll give the rest time to Sebastian.
Yeah, thank you very much for the invitation to speak today. And I've changed the title slightly from what was advertised. Essentially, I will be using tungsten isotope to sort of refuel the debate about where kimberlites come from. Do they have an upper mantle origin, or do they have a lower mantle origin, as has been proposed quite frequently? So I will be talking about kimberlites in general, but use new evidence from tungsten isotopes for these rocks in particular. And what you see here in the left bottom corner, that's a typical kimberlite from the type locality in Kimberlites, South Africa. And you see a lot of fresh olivine. You see there's not a single grain that looks like similar, so they're all different. It's a very complex rock, and it was first described more than 130 years ago by this gentleman here. And it's fair to say that more than 130 years later, we are pretty much still as puzzled as we were back in the day about the origin of these rocks. So there's still a lot of big question marks, how these things form and how they come to the surface. Just going to the next slide. Might just take a moment. I have to get out of this. Somewhat frozen. Let me just, okay, now here we go. Good, so now we're in business. Just some quick acknowledgements. Those are all institutions that have either supported my research as project partners, which is the top panel here, or as sort of funding partners or donors of samples, which is the bottom part here. And for the tungsten work in particular, we have received generous support by the European Research Council. And all of this work has actually been done in Germany in collaboration with Andreas Stracker and Thorsten Kleine in their labs. So kimberlites, we find them on every continent. This is just sort of a summary on where we can find kimberlites. Sort of you see here the examples from North America, Asia, China, Australia, and obviously sort of southern sub-Saharan Africa. And if you kind of know the geology of the world, you can see that they beautifully outline the continental shields, sort of the shields, and in particular the cratons, like here Northern America, also here the Siberian craton, and then here the Kalahari and Kapwal cratons. So they're somewhat tied in their origin to thick and old continental lithosphere, and that's a detail that's very often overlooked in models that try to explain this type of magmatism, and models that try to put these rocks into the very lower mantle that has absolutely no connection to the surface geology. So I will be sort of addressing this issue later on during the talk. This is just an artist's expression from some 20 years ago. Sort of a local artist in South Africa was drawing these sort of paintings, and people are sort of fascinated with making kimberlites sort of very extreme and very hot magmas associated to plumes, and how they sort of rise with ultrasonic speed all the way through the cratonic lithosphere to surface, sampling all the sparkly stuff here, which is supposed to be lithospheric diamond. But then there's also other sparkly stuff here, which is supposed to be ultra deep diamond or sublithospheric diamond. Clearly, it's not quite that extreme, but we will get there. So how did this all start? To understand a little bit more of the origin of kimberlites by using isotopes, this goes back to this seminal paper by Craig Smith from 1982. That's now 40 years ago. And he was the first one to measure isotopic compositions for type kimberlites from South Africa. And that's what he came up with in the classic neodymium-strontium isotope diagram. A couple of data points that made it actually into Nature by that time. And what he could show was that there is a slight depletion in these magmas. Sort of they have positive epsilon neodymium values, but they're not very far removed from the bulk earth composition. So they're not as extremely depleted as the morph source mantle, but they show a mild depletion, very similar to ocean island basalts. And that was the big discovery by that time, the similarity to ocean island basalts. And this is now 40 years later, a data compilation from just a few years ago, where we add to the neodymium information, neodymium isotope information, we add the hafnium isotope information, and we see for the global kimberlites here that we get the mild depletion, but also mild enrichment, but nothing has really moved very far away from bulk earth compositions. So in a way, these magmas are isotopically actually not that extreme. So the ocean island basalt kimberlite link is important because it has shaped many of the genetic models for kimberlites, mainly because there is some sort of agreement that many of the larger ocean islands are sort of plume sourced or plume fed from the lower mantle. And this is just taken from this cartoon by Kellogg. And you see for the oceanic island basalt source, very often we have these lower mantle plumes from near the core mantle boundary, sampling some sort of more primordial, lower untapped mantle. And by the same token, with the analogy in strontium, neodymium, and also hafnium isotopes, kimberlites on the continents, which are not sort of put into this image, have also been quite frequently proposed to have such ultra deep origin. So throughout the talk, I will be using upper mantle and lower mantle quite frequently, and I'm not so sure about the audience, but for the purpose of this talk, we just put the boundary somewhere at 660 kilometers, so the transition zone separating that region, sort of just to set the scene that everyone knows what I'm actually talking about. So the roadmap for today, first, I would like to show some evidence that may exist for a lower mantle origin of kimberlites. That's on the one hand, the existence of so-called ultra-deep diamonds that are not from the lithosphere, that are from deeper. And then also the evidence that may come from the so-called plume generation zones, or the low velocity shear zones at the core mantle boundary, and in particular the one that's prominent beneath the African continent. Then after that, I will briefly review the evidence for an upper mantle origin for kimberlites. And under that sort of under that heading, the tungsten-182 evidence fits very nicely into that. And then I will also say a few words about the formation of carbon dioxide-rich magmas, which actually also supports the upper mantle origin much more than a lower mantle origin. And that shall lead me to my preferred model. So for the first part, what are the signs for that kimberlite magmas could actually come from the lower mantle? And for that, one really needs to look at the diamond content of some kimberlites, not all kimberlites, but some few kimberlites. And on the one hand, we have these beautiful euhedral shaped diamonds, as you can see here. They show very nice crystal phases, and they're very typical for diamonds from the deeper lithosphere. So those formed in less than 250 kilometer depths, which is known from the inclusions that they sometimes contain. Garnet, pyroxenes, olivine, and so on. So we know that they have sort of a lithospheric origin. Just on a side note, this little seed here, which is a typical African plant, the so-called carob seed, coming from this sort of fruit, that was used more than 100 years ago as the measure for 1 carat, because it has approximately that weight. And before balances were around in those mining districts, people just used the seed sort of to figure out what the size of diamond is. That's where the word carat comes from this seed, carob, just sort of out of interest in case anybody wonders. So another group of diamonds that is more spectacular in a way than the lithospheric diamonds are the ones that form in the convecting mantle or even below, sort of, let's call it the sublithosphere for now. Those look like this, and you may have already noticed we are lacking the euhedral shapes. There's no real crystal faces. All you see is sort of broken cleavages here, and sort of a lot of resorption. So those things have suffered quite a bit. And from inclusion work that has come up just over the last 5-6 years, we know that they form somewhere between 250 and 800 kilometers depth. So that's where we actually poke into the lower mantle, into the uppermost lower mantle. And the reasoning in many studies is if you have diamonds that at some point have seen that depth, then the kimberlite must also come from that depth or below. And that means kimberlites have a lower mantle origin. And I tried to convince you that this logic is not quite as simple as that. Those particular stones here come from a mine called Letseng, that's in Lesotho, which is this little state that's sort of engulfed by South Africa. So those are actually diamonds from beneath the Kapval crater. And they have become quite famous over the last few years since the work by Evan Smith here from 2016, who could show that a lot of these dark specks that you can see in some of these diamonds actually not graphite, that they are sort of these metallic inclusions where we have sort of metal alloys, but we also have carbides. So very complicated, very reduced phases. And this was on the one hand evidence that they come from somewhere below the lithosphere, but also that the convecting mantle is quite reduced below 250 kilometers to enable the crystallization of such reduced metallic phases. That's what this locality looks like. It's just out of interest. That's Letseng in Lesotho. Most of the country rocks that you see here are actually Jurassic flood basalts of the Karoo supergroup. And Letseng itself has two pits or two pipes that are being mined. It's this one, main, and then that's the satellite pipe that are being mined mainly for these super deep, ultra deep diamonds, because Letseng is famous for having actually the lowest diamond grade in these rocks. The diamond grade is almost as bad as in the basalt, except for every 2 or 3 years you find these spectacular stones that I've just shown here, which makes it worthwhile for mining. Yeah, so there's the one thing when we talk about ultra deep diamonds that they actually rather shallow. So I just say it like that. But if you see in this diagram that I've drawn to scale actually, where you can see depths below surface. So that surface here at 0, and here we go all the way 3,000 kilometers down to the core mantle boundary. And the deepest known diamonds that we so far have sort of tap to 800 kilometers just below the transition zone. Excuse me. And if we look at the inclusions, not just for these diamonds that have sort of lower mantle paragenesis, also for the ones with transition zone paragenesis or sort of lower upper mantle paragenesis, we just look at sort of majoritic inclusions, ferropericlase, bridgemanite inclusions, and also calcium-rich perovskite structured inclusions. And if we look at these diamonds' carbon isotopic composition, which is the x-axis here, we see that quite a few extend to very low carbon isotopic values, which tells us that that is mostly recycled material. Some stick here at the canonical mantle value at -5 delta carbon 13, but the vast majority is really recycled material. And the same can be said for the lithospheric diamonds, which is this bar here. So that stops at 250 kilometers. A vast amount has actually mantle value, but we extend all the way to -40. So there's also recycled components involved. So the whole kimberlite diamond system seems to sort of just recycle within the upper sort of 800 kilometers. And we hardly ever tap into the lower mantle. That's why I put the big question mark in here, because we know very little of what's actually happening in this region based on natural samples. So another line of reasoning why kimberlites are fancy to come from the lower mantle or from the core mantle boundary in some models is their seemingly strong association to these LLSVPs, or large low shear velocity provinces. And in this case, I've just plotted the African one. That's the outline here. And it sits essentially at the top of the core mantle boundary and forms compositionally anomalous material that sort of can be detected seismically by low shear wave velocity provinces. And about 85% of the world's kimberlites, that's all the red squares here, they tend to cluster along the margin of the LLSVP, some also sort of within it. So there's some sort of a geographic association between kimberlite magmatism and at least the African LLSVP. This has been put forward initially by Kevin Burke, then sort of pioneered by Trond Torsvik, and we have been used this sort of diagram over and over in other publications. This has to be taken with some grain of salt, because there are other studies like this one here from 2015 that have shown that this could also just be a spurious correlation because of the strong north-south orientation of this African LLSVP. It's also a rather large feature, which makes, if it by coincidence just sits below the African plate for most of the Phanerozoic, then pretty much any kimberlite that is being generated beneath the craton would pretend to have an association to this rather deep-seated feature from more than 2,000 kilometers below Earth's surface. So there are arguments that this could be just sort of a spurious correlation. So just in case somebody's not familiar with what these LLSVPs are, I've taken some images from the literature. They typically interpreted as dense, hot primordial material at the core mantle boundary. In those images, we look at the surface of the core, which is the red material here. And the African LLSVP in this case sort of wraps around it like that. You see it's quite significant in size, and that would be the antipodal one beneath the Pacific. And in blue, those are just subducting slabs that go down all the way to the core mantle boundary. And ordinary ambient mantle is just sort of completely removed from this image. So just to set the scene, core mantle boundary, CMB, just in case you wonder, and then the LLSVPs, the large low shear wave velocity provinces. So this means that if kimberlites really have an origin from the lower mantle and from these sort of plume generation zones or LLSVPs, one would need to find some form of geochemical tracer that has the potential to trace any anomalous mantle that's close to the core and has sort of seen core entrainment, or any primordial material that's just being stuck somewhere in the lower mantle near the core mantle boundary. And by the same analogy as the OIBs that form beneath the Pacific, in this case, beneath the Pacific or above the Pacific LLSVP, many workers have proposed that all this African kimberlite magmatism is somewhat sourced from the core mantle boundary as part of the African LLSVP. And that's just another cartoon of all the kimberlites during the late Cretaceous here, 90 million years ago, how they sort of tend to cluster along this western wing of the African LLSVP. So the question is, from a geochemical perspective, can we trace anything from the core? Or if not from the core, can we trace anything primordial? And that could be any form of magma ocean remnants that are sort of trapped or incorporated into the African LLSVP. So now we will be getting closer to the tungsten data that we have produced for kimberlites. And I'm sort of already using this actually as evidence for an upper mantle origin of kimberlites. So the one geochemical tool that we have been given over the last sort of 10, 12 years is the hafnium tungsten isotope system. And I've just used this avocado here sort of to give you an idea again of the core, sort of the mantle, and then the lithospheric component here, the lithospheric mantle, and the dark green here that's supposed to be the crust. You can see that hafnium is a lithophile element, rock-loving, really occupies most of the mantle and then also the crust, does not really partition into the core, and tungsten is a moderately siderophile element. It likes iron and metal, and it would, during core segregation and core formation, be preferentially drawn into the core and separated from the hafnium that stays back in the silicate earth. So this goes back, obviously, to Victor Moritz Goldschmidt, just sort of as an educational thing on the side. So the beauty with that system is that it can trace hafnium tungsten isotope system. It can trace any form of really ancient mantle components or components in the mantle that have been contaminated by material from the Earth core. And I will explain this in a second why this is. So that's sort of the nuts and bolts of the hafnium tungsten isotope system. Mass 182 hafnium decays to mass 182 tungsten. And it does that relatively fast with a half-life of only 9 million years, which means if you look at this graph, which is 182 hafnium over 180, you can see that 182 hafnium is decayed away pretty much after 50 to 60 million years. So into solar system formation. That means after solar system formation, core segregation that started 60 million years into these processes, this ratio here, the tungsten-182, 184 becomes a stable isotope ratio, and there's no more radiogenic ingrowth, which means that most of the silicate Earth is in theory quite homogeneous in its tungsten isotopic composition. And the trick will be to find rocks or minerals that still preserve anomalous tungsten-182 that goes back to early processes from more than 4.5 billion years ago, which includes the core formation and then any sort of contamination that the mantle may have suffered later on by core leakage and so on. So what we measure is this ratio, and the last 10 years, 5 to 10 years, have seen a revolution in measuring this ratio very precise, because this is really what matters, because we look at extremely small differences on the 6 decimal place in this isotopic ratio. And that's why this notation is being used, the mu-182 tungsten, which really amplifies the isotopic differences on the 6 decimal place at ppm level. So you will see this a lot, mu-182 tungsten, which is the classic isotope notation, just looking at small differences on the 6 decimal place. Going to this graph here on the left-hand side by Jones and colleagues from just a few years back, they essentially came up with quite a clever model on how one could explain the few isotopic anomalies for tungsten that are being measured in terrestrial rocks. And by the time, the gray field here, this was sort of the isotope compositions that were known from terrestrial rocks. Remember, if the isotopic composition is mu-182 0, that means it's completely normal. There's no anomalous tungsten in this rock. So we start talking about anomalies for anything that's sort of plus minus 5, different from 0. And you can see if we touch down here on minus 20 on this early study, all the way to plus 40, those are quite significant tungsten isotope anomalies. So Jones et al. Modeled quite elegantly that core contribution less than 1% can actually draw out terrestrial magmas very quickly to very negative values, because the Earth core would be sitting somewhere here at minus 220, sort of off the scale. So it's very negative in its tungsten isotopic composition, and the smallest amounts of contamination of mantle material with core would result in negative tungsten isotopic compositions in these magmas. For positive anomalies, we would need more of an exotic component, but in all fairness, one also has to say that the upper end here is probably not quite real anymore, that the most positive values we kind of aware of probably also just around plus 15 to plus 20. So this group here around Andrea Mundel from Maryland, now in Vienna, she has been very ambitious and measured a lot of ocean island basalts. You can see here Hawaii, Samoa, and all these famous OIBs. And she has systematically measured them for their tungsten isotopic composition and found for most actually quite significant negative tungsten isotope anomalies, definitely outside the minus 5 bracket and reaching from minus 10 all the way to minus 20 in some cases. And her interpretation from this paper from last year was that the OIB source is sitting in the lower mantle. It is sort of part of the realm of the LLSVPs, and it's drawing core material into this lower mantle source and essentially becomes core contaminated, the lower mantle source. So this was the preferred interpretation for this tungsten isotope data set for global OIBs. And just to sort of put this into a little animation taken from Brandenburg's paper, you just see in this force balance plate models the typical recycling effects of mantle convection, subducting slabs going down, replacing material near the core mantle boundary that causes some form of lower mantle material going up in the form of plumes and so on. And just to remind everyone, the core sits at minus 220, mu-182 tungsten, and the majority of the silicate earth sits at 0 plus minus 5, which is the analytical precision that we can measure sort of terrestrial rocks. So very negative material really polluting here the lower mantle, and any magma that should come from here should also pick up negative tungsten isotopic signatures. That was the motivation for the study, to see if kimberlites actually come from the lower mantle. And to this end, we have selected a whole bunch of kimberlites from the realm of the African LLSVP. If you look at this image here, that's sort of the African LSVP. This is the African outline of Africa as a continent, but it's at the time slice of the late Cretaceous, around about 100 million years, with an error margin, sort of a plate reconstruction. You see that's sort of the beginning breakup of Western Gondwana. And we have selected all these red samples here. Then we have also selected a few older samples for which we don't really do plate reconstructions. But you get a good idea that we have a good coverage of the African LLSVP. Those are all the localities that we selected. This is pretty much the Champions League of African kimberlites. Many of those with an asterisk here, are actually localities that have produced super deep diamonds through mining activities. The ones that I showed earlier from, for instance, Letseng, as an example. So if we look at fairly conventional isotope systems like the neodymium and the hafnium isotopes, this would be our selection of samples here, everything that's in red and blue, and that's just comparing it to the known Group 1 kimberlite database. So it's a fairly representative selection of samples, covering sort of samples from within the mantle array, but also those sort of enigmatic ones that fall below the neodymium hafnium mantle array. And so we are quite confident that we haven't really missed any important sample in this sort of exercise. And that's what our data look like. So if you just zoom in on the left-hand side here, everything that has a color has been measured during this study, and everything that's sort of without color, that's literature data. And so to make a long story short, we haven't found a single tungsten isotope anomaly in these African kimberlites. That includes the very young ones here, which are essentially quaternary in Tanzania, but it also includes the older ones, the early Proterozoic ones. So there's no evolution through time or anything. Everything is within uncertainty of 0. So which means we have a very hard time finding any evidence for a lower mantle origin for the kimberlite magmas themselves, not to speak of anything that would come from near the core mantle boundary. And just blowing this up on the speed panel to the right-hand side, you see each dot that's represented here in color has been measured on different samples. If you just take the Letseng example, you see we have taken 5 samples here and measured them numerous times. And that's sort of the individual results before we average them out. So we have done a fairly thorough job. And I don't think that for these particular samples that picture would change very much in this case. So if one measures tungsten, one should probably also say just a few words about the actual concentrations of tungsten in these rocks. And you can see in this gray box here, that's the content of the tungsten hour samples from those African kimberlites. And you see that it goes from sub-ppm level, that's 1000 ppb, that's 1 ppm, sub-ppm level to a couple of ppm up to 10 ppm or something like that. So it's quite variable. And initially we were a little bit surprised why there's so much variability, but it makes a whole lot of sense if one just takes melting models for a melting of carbonated peridotite. And we take here the partition coefficients by Dasgupta and also by Bray for carbonatitic and kimberlitic melts with very low silica content at the conditions of the convecting upper mantle. And it's just 2 different color codes for the 2 models. And you can see that that is sort of exactly the range of compositions one would expect for low degree melting of carbonated peridotite. That's sort of 0.1% melting to 3% melting. And we can pretty much explain the entire range of tungsten content in our samples. On that note, I would like to mention that initially I introduced tungsten as a moderately siderophile element, but now with that melting model, you can actually see that it behaves highly incompatible, quite similar to uranium and thorium in its compatibility, which means that in the absence of any metal, tungsten is actually a highly incompatible or lithophile element, and that's why it also gets heavily enriched in the crust. So that's important to bear in mind. And one can also use this diagram as evidence for the tungsten content in the kimberlites to argue that the kimberlites must come from carbonated upper mantle where there is no metal, because in the absence of metal, it really gives you these concentrations at very low degrees of melting. And these low degrees of melting we need to explain all the other incompatible elements like the light rare earth elements, niobium, and so on, to get the enrichment levels that kimberlites typically have. So this all neatly fits together in a geochemical sense. So this brings me to the preferred model, sort of to sum this all up. And the preferred model starts with some form of petrology, because in the end of the day, the petrology is what controls everything, and the isotopes sort of just a convenient tool to confirm or to disprove some models, but the petrology is the basis for everything. So this is a simple pressure temperature diagram. And what we have done here is we've plotted experimental work for high pressure experiments that used volatiles and produced melts with less than 25% silica. So everything in blue is carbonatitic to kimberlitic in composition, and then everything in red has more than 40% silica and is also sometimes dry in the experiments. And that's more basaltic to komatitic melts. And in this diagram, and plotting different solidi curves for oxidized mantle and also for dry and reduced mantle, we can see that things like kimberlitic and carbonatitic melts would always be forming at relatively low temperatures because these volatiles suppress the solidus, and they sort of form near normal ambient convecting mantle geotherms, like 1300 degrees C here, maybe all the way to 1400 degrees C. So this is pretty normal average mantle temperatures that can produce these melts, and no real heat anomalies are needed, not the same type of heat anomalies that we need to feed flood basalt eruption, certain ocean islands, or the komatiites back in the Archean and Proterozoic. So the petrology already dictates that kimberlites are actually cold magmas, and no hot lower mantle plumes are really needed for this type of magma. So this can be sort of brought into the cartoon by Steve Shirey here, who has summarized sort of different tectonic settings around cratons and the cratonic root itself. What we have added to this diagram is this red field here for kimberlites. Sort of, we think that the majority of kimberlites form at the base of the craton, 250, 300 kilometer depth, at this interface between the convecting mantle and the cratonic mantle. And that's from where it can sample a lot of these lithospheric diamonds that you've seen, but it has also an opportunity to sample the ultra deep diamonds, which just by convection, sort of, they usually get sourced from downgoing slabs, and convection just brings them back and sort of subcretes them to the bottom of the craton. And from here, they can be sampled. So we don't really need anything from below the transition zone to directly come up to the surface. Sort of this sort of part of the mantle system is enough to create kimberlites and most of their diamond content. And that being said, the main challenge to actually get kimberlite eruptions at surface is probably not so much to make them in the mantle. That seems to be a relatively easy process. Yeah, volatiles are there, temperatures are fine to make those magmas, everything is there. The one problem that we have is really bringing them through the lithosphere without completely reacting them out. And that's where the plate tectonics come into the game, and where we decouple the origin of kimberlites from the plume paradigm, but rather say, well, this is all controlled by plate tectonics. Because if we look at this diagram, we can see for the African kimberlites that formed over the last 300 million years, they're plotted here as some form of histogram. And in the same diagram, we plot the plate velocity just for the African plate over the last 300 million years. And for the two biggest pulses of kimberlite eruptions, at 900 million years and the one here at around about 120, 130 million years, we see that the African plate has always come out of a sort of stagnant phase and started to jog and accelerate. And it does the same here, it starts to accelerate. So it's really the plate moving, changing direction and changing speed, what reactivates lithospheric, deep-seated lithospheric faults and lineaments. And that really helps these magmas that sit just below the cratonic lithosphere to pump them up to surface according to this data. So you can ask me a question what's going on here, but this is more complicated, mainly because before 180 million years, that's about here, most of the African plate is actually covered by the Karoo supergroup. So we actually don't see many kimberlites of that time slice. And I could just sort of postulate that there's probably much more kimberlites of that age group. It's just all covered by basalts and sediments of the Karoo supergroup. Okay, so that are the main take-home messages from this sort of exercise. So I've shown you some of the first high-precision tungsten-182 data for African kimberlites. And at this point in time, they do not support a lower mantle origin for this type of magmatism. The petrology of kimberlite magmas itself calls for convecting upper mantle sources. This would be sort of the most reasonable model, in my opinion. You don't have to agree with that. And for the rare ultra-deep diamonds that give us a headache, sort of how this all fits in with the kimberlites, one can interpret them just as stranded below the cratonic lithosphere, just by normal mantle convection to sort of sit there. This process of stranding can, in theory, even be an Archean or Proterozoic process. This does not have to happen recently. So they can have been sitting as part of the lower lithosphere for a very long time. So those are the three main take-home points. And with that, I finish my talk and I'm happy to take questions.
Great. Thank you very much, Sebastian, for the talk. And now it's time for questions from the audience. Feel free to raise a hand or directly open your mic or type your questions, and I could help you to ask a question. Well, I could have two relevant questions. I think it's quite a it's a really interesting story, and with quite a compelling evidence. So one question is related to carbonatite, because one way to think about it, as you also referred to the, for example, uranium origin coefficient as a proxy for tungsten. So I was looking for the tungsten concentration at carbonatite. I only surveyed SLM 2020 Science Advance, but that work didn't measure tungsten. So may I know that in your knowledge that does the carbonatite has very high, relatively high tungsten concentrations?
I'm not so familiar with carbonatites and their tungsten content, but but you could reason that most carbonatites are quite enriched in uranium, so they should also be quite enriched in tungsten. Sort of the partition coefficients between low degree mantle, sort of peridotitic mantle in the presence of volatiles, and low degree melts for uranium tungsten are very much the same. So yes, you would also expect high tungsten content. The one thing one has to be very careful of is how much interaction and contamination by the continental crust affects any of these magmas, including the kimberlites and also the carbonatites. They're not protected from that, right? Sort of, they have to go through continental crust, and the continental crust is very enriched in tungsten. So some of the tungsten carbonatites might even come from the continental crust. That's something we have learned from lead isotopes. A lot of lead isotopes in carbonatites give us continental crust signatures, which means certain elements get stripped from the continental crust more than others, right? And tungsten is probably also a candidate for that. For the kimberlite story, if I link back to that, you could say, oh, how about all your tungsten comes from the continental crust? The beauty with that is that kimberlites are tied to the Archean cratons, and the Archean crust actually shows quite a lot of tungsten isotope anomalies with the early crust. It's both the TTG basement, which has positive anomalies, but also some of the komatiites. Sort of, there's hardly any early Archean rock that doesn't have a tungsten isotope anomaly. So if our tungsten in the kimberlites would have come from the Archean continental crust, that should have also created isotopic anomalies, which we don't see. Yeah.
So, question from Yuan Li: that was the oxygen fugacity of the kimberlites?
Well, we don't really know what it is like when it forms, but at surface it's definitely quite oxidized, right? But not more oxidized than basalt, sort of. I mean, there's carbonate in the system, lots of water and carbonate. It's somewhere around FMQ, sort of. A typical diamond wouldn't be very happy in a kimberlite. And a lot of the diamonds also show that they're not happy, right? Sort of, even the lithospheric diamonds very often show these negative trigons, these dissolution edges and dissolution pits. So if the process of kimberlite magma ascent takes too long, it can be very detrimental to diamond, even upon ascent. So because it is a relatively oxidized magma.
Okay, next question. I think it's from Chen Ling from Institute of Geology and Physics. How thick is the cratonic lithosphere for the generation of kimberlites, and how does the lithospheric mantle affect the kimberlite geochemistry?
Yes. So for the areas where we have, where there are proper kimberlites, the lithosphere is usually thicker than 120, 140 kilometers. It does not always have to be diamond stability field, sort of 150, 160 kilometers, but you need at least 120 kilometers. If it goes below that number, the mantle below, the pressure PT regime really promotes more extensive melting, which leads ultimately always to basalt. And you guys know this from the North China Craton, that for most of the Mesozoic and Cenozoic, the magmas that come through what's left of the North China Craton is basaltic, and you only have kimberlites during the Ordovician, when there was still a little bit of a root left, or when there was some root. So anything from 120 to 250 kilometers. And the 250 kilometers, that mainly comes from the diamond inclusions of lithospheric diamonds. They really don't go much deeper than that. If they go deeper, we're really already in the convecting mantle. So it's fair to say that this is sort of the depth range that we deal with. And the lithospheric mantle plays a huge role for the kimberlites in giving them sort of their final composition. If they start out as sort of clean carbonated silicate melts, maybe with something like 15-20% silica, when even the least contaminated kimberlites end up at surface, they typically have 30% silica, so they gain sort of mostly 10-15% SiO2, and that's coming mostly from the dissolution of autopyroxene in the cratonic mantle. Sort of interaction, they're eating their way through the cratonic mantle, and by that they lose carbon dioxide, but they gain silica. So that's sort of the main game changer for them. There are these ideas that they really start out as pure carbonatites, but that is also very difficult because a pure carbonatite melt, a low volume carbonatite melt, would thermodynamically not really make it all the way through that 250 kilometer thick lithosphere. So there's probably some silica involved from the beginning. But long story short, the cratonic mantle is important in shaping the composition of kimberlites, and obviously then also adding all the diamond from where 95% of the diamonds come from.
Okay, the next question is from an undergraduate student. And could you go to the partial melting
Yes.
and constant concentration figure? And
Yes.
the students is asking for the clarification of the two curves. Yeah, the two partial melting curves, because he doesn't understand.
Yeah, so on the y-axis, we plot just the tungsten content in ppb. So if you look at 1000 ppb, that's 1 ppm. And that's it. Then on the y-axis, we have the melting degree, and that would be 10% here, 10% melting of carbonated peridotite. So that's peridotite that's being fluxed by carbon dioxide fluid, right? Sort of 10%, 20%, 30%. 20, 30% melting, that's pretty much sort of making flood basalts, right? And for kimberlitic carbonatic systems, we typically look at melting degrees below 5%, so anything below here. And in our model, sort of, we prefer this. This is sort of the melting degree of this carbonated peridotite. The peridotite itself has, as a starting composition, we use primitive mantle, so neither particularly enriched nor particularly depleted, sort of just coming with a primitive mantle composition for tungsten. And then we use the partitioning results from these experiments. And that's by Raj Dasgupta's work, 6.6 to 8.6 GPa. So that's about 200 kilometers to more or less 300 kilometers. So that's 10 GPa, that's 300 kilometers. So we're looking at conditions just below the cratonic lithosphere into the uppermost convecting mantle beneath the craton. So extremely relevant to kimberlites, actually. And both of them come up with slightly different numbers, but the story is pretty much the same, that in Bryce's experiment, we get something like 200, 300, 400 ppm tungsten, which many of our kimberlites have. And in Dasgupta's experiment, we get a couple of ppm of tungsten, which some of our samples have. So that's pretty much the story. What I have to say here, and that's sort of where this whole thing is a little bit cheating, none of these studies has actually data for tungsten partitioning experiments. We have taken the partition coefficients for uranium because there is work, especially from Bill McDonough's group, who have shown over and over again that tungsten has the same KD as uranium in silicate systems whenever there's no metal involved. So unfortunately, there is not so much tungsten partitioning data, unless I missed something from the last 1 or 2 years.
Yeah, it is lacking. Actually, it's quite good to verify that whether sulfides coexisted with the carbon-rich melt, since people did claim other evidences to claim that the sulfides do exist.
In the source, or yeah, I'm sure that there.
Yeah. Yes, and I would add one thing to the explanation because these two curves that Changyu was asking about, they are from the experimental petrology work, and so they fix a composition, and then they use different temperatures. So we could see the x-axis actually is related to temperature. Yeah, it's controlled by temperature, which people could control by their experiments. And the melt fraction could be calculated by the mass balance when we're measuring the melt composition and the residual solid compositions by electron microprobe. Okay. Actually, I have another question. Not directly related to this science, but more to data source. So in your earlier plot that you showed the global kimberlites, and among them, in my recollection, that more than 1,000 has the ages of kimberlites, and that is also in the in your previous publication. May I know that that's all the kimberlite that with age contain the xenoliths that has been published? What could be traced in literature?
Not all of them contain xenoliths. So you have to remember that most kimberlites are not really accessible to the sort of field geologists. They're covered, they're very often just drilled or then exposed through mining. And those few, they're sort of on the world, 60 to 70 mining projects, right? Mm-hmm. Which is not a whole lot. And at some point, those will produce xenoliths just by industrially processing hundreds and millions of tons of kimberlite. The odd kimberlite dike somewhere in the middle of nowhere you will have a very hard time finding sizable xenoliths. So the picture is a little bit skewed toward these tailing stumps from mines, right? But that accounts only for a couple of handfuls of kimberlites. So the same is true for the diamonds. Only 10% of all kimberlites actually have diamonds. 90% are barren. Barren meaning less than 1 carat per 100 ton, which is pretty much the same as a basalt. Yeah. So not every kimberlite has a diamond. That's also a misconception.
It's rare for kimberlite that has diamond. However, when we look at the georock data base, for example, when I counted, it's like because it's underreported, very likely, and also there's overrepresentation of diamondiferous kimberlite. It's like a half or third of the kimberlites that has diamonds reported from georock database.
Georock, but we know from exploration data that sort of the ballpark number, 10% are diamondiferous. And the definition for diamondiferous in this case is 1 carat for 100 tons of kimberlite. So if you have less than that, that is really extremely low diamond grade, and some have nothing, right? So which really means having highly diamondiferous kimberlites is still quite the exception, even among kimberlites. Yeah.
Mm-hmm. Yes, and actually, when I do the calculation,
but because you are very interested in data science and these things, the one main problem, including the geochronology database, is that there is always too many localities measured heavily and just a few not measured at all. There's not really a fair weighting of the data that you say, okay, there should only be one age for each cluster, right? You have you have some kimberlite clusters in Botswana. They have 5 or 6 mines, and they're heavily studied, which means they're also heavily dated, and they sort of swamp the databases with data, right?
Yes, for the unbalanced data set, there are the statistical methods that could improve it. But I agree with you that if the, especially for the scarce parts of the data that are too lacking, then the resultant model is much less reliable.
Yeah.
Okay. More questions from the audience? Or I think we are running perfect timing and 1 hour show. So thank you again, Sebastian, for giving a talk, and thanks everybody for participating.
Yeah, thank you very much for having me. I enjoyed it.
Yeah, thank you. Thank you for the talk. Thank you very much. Have a good day.
Yeah, you too. Thanks. Bye, guys.
Bye-bye.